Alright folks, this is the first video of chapter 2 and it's about the first topic, nature of light, and we will talk about the wave nature and the particle nature of light. And this slide shows you some very basic properties of light and sound. Both light and sound are two types of energy, okay? And in this picture shows you the light can travel very fast. The speed of light is 3.00 times 10 to the 8th meter per second. And for sound, it's still fast, but it's much slower than light. The speed of sound is 340 meters per second. And that is why during a lightning storm, you always see the lightning first, and then hear the thunder. Okay, so that's the reason, because sound travels much slower than light. All right. Now let's talk about the wave nature of light. Okay. First, let's discuss what the wave would look like. Okay. Well, if you go to the beach, you will see those the ocean waves probably. Okay, so wave has two features. The first one is the wavelength. The second one is the amplitude. Well, the first one, the wavelength, is the distance between the two crests. Okay, and the amplitude is the baseline of the wave. The distance between the baseline of the wave and the crest. Okay, so this one is an amplitude, and for sure, certainly that's if you have a larger distance between the crest and the baseline, then the stronger the wave. Okay, all right. So this is the wave. And another thing about the wave is the frequency. What is a frequency? I think this picture tells us some important connection between frequency and wavelength. Okay, well, frequency is defined as the number of the wave crests that pass through a stationary point in a given period of time. All right, so you can see from this picture you have three boxes. Okay, the red box here has two crests. Okay, one full crest here, one half and one half. So total, there are two crests. And in this yellow window, you have three full crests, one half, second half crests. So you have total four crests. And in this blue window, you have five crests. Okay, so in the same amount of time, this window has two crests, four crests, five crests. So based on the definition of the frequency, we know that this wave has the highest frequency because you have more crests than the other two windows, right? And this one has a smaller frequency than the blue window, but higher frequency than this one. And the red window, of course, has the lowest frequency than the other two among the three. Okay, and if you take a look at the wavelength of those three waves, for the red window, the distance between the two neighboring crests is quite long. And for the yellow window, the distance between the two neighboring crests is shorter than this red wave. Okay, and for the blue window, the distance of the two neighboring crests is the smallest among the three. Okay, so it looks like the red wave has the longest wavelength, the lowest frequency. The blue window has the shortest wavelength, but the highest frequency. Okay, so you can notice now that between the frequency and the wavelength, it's inverse proportional to each other. Okay, so how do we define this kind of connection between the wavelength and frequency? Here is the mathematic equation for us to use. We use nu to represent frequency, and that equals to c over lambda. Lambda is the frequency, and c is the speed of light. Okay, let me make a note here. Capital C is the speed of light, and from the previous slides, okay, that is 3.00 times 10 to the 8th meter per second. Sometimes you see textbook using 3.0 instead of 3.00, but it doesn't matter. Okay, you can use both, and we don't need to worry about the significant figures of those constants anyway. All right, so this is a mathematical connection between the frequency and wavelength. What's the unit for frequency? Well, the unit of the frequency is the either 1 over second or hertz. Okay, hertz. And for lambda wavelength, the most common unit for lambda is, let me write it here, is nanometer. But of course, you can use centimeter, you can use picometer, and it really depends on what frequency, what wavelength or what frequency you are talking about. Okay, but nanometer is the most common unit for wavelength. Let's just do some very quick practice. Okay, so let's calculate. I'll write it here. Calculate the new frequency for a light between a light beam with lambda equals to 34.0 nanometer. Okay, well, what you need to do is just plug those data into this equation and then calculate. I'll write on this side. Okay, so nu equals to, remember, on top is the speed of light, 3.00 times 10 to the 8th meter per second. Okay. The bottom would be the wavelength. One thing I do want to remind you is the unit. Remember, the speed of light, the unit is meter per second. And for the wavelength, the unit is nanometer. So we have to be consistent to cancel the meter, okay? To cancel the meter or nanometer to get the second, 1 over second, which is the unit for frequency. Okay, so we have to be consistent. You can either convert meter to nanometer or convert nanometer to meter. It's really a personal preference. For myself, I prefer to convert the nanometer to meter. So 34.0 nanometer, okay, converts the nanometer to meter. We know that's 1 nanometer based on the prefix multiplier. Lower nano, okay, represent 10 to the negative 9, 10 to the negative 9 meter, okay. I want you to be familiar with those kind of prefix multiplier. All right, now let's continue our calculation. If you do the calculation here, you will have 8.82 times 10 to the 15, 1 over second. Okay. Remember, how do we get this 1 over second unit here, which is also hertz, the unit of frequency. Okay. Let me show you. Well, nanometer get canceled, right? And meter will get also canceled. So whatever left for the unit is going to be 1 over second. That is how we get the unit. And also because the wavelength is 34.0 nanometer, 3 significant figures. That's why we keep 3 significant figures for the final answer. Okay. Okay. So this is the connection between the wavelength and frequency. One thing I want to mention here is this picture. This picture shows us the difference between the dim light and bright light. We are talking about the same lights, okay, because they have the same frequency. Okay, both examples here you have two crests. Okay, and so that means they have the same wavelength and same frequency. But for dim light, what's the difference between the dim light and bright light? It's about the intensity, which is the amplitude. Okay, so for dim light, the amplitude is much smaller than the amplitude of bright light. Okay, so it's sort of like you talk to someone with a louder voice or weaker voice. The voice is still from you, right? Same sound, same voice, but with a stronger voice, you have higher intensity. With the weaker voice, you have lower intensity. Okay, so that's the difference between these two. All right. This slide shows us more examples about the wave nature of light. Well, you can use a prism lens to split visible light into essentially a rainbow. Well, in this rainbow, okay, visible light, in this rainbow you can see that different color has different wavelengths. Okay, and this lady is wearing a red shirt. Why do we see red color? The reason is the dye compound in this lady's t-shirt. Remember, when you make a t-shirt, in order to make a show a certain color, you have to use the dye compound, DYE, okay, compound. And this dye compound will absorb all the other light, all the other colors from the visible light and only reflect red color. That's why we see red color. And of course, if you are wearing a blue shirt, then that means that dye compound in that blue shirt absorbs all the other colors, only reflects blue light. Okay, that's the reason. The last picture here is infrared light. Infrared light has a lower frequency than visible light. Okay, and our eyes cannot see infrared light, but by using special instruments, you can use infrared light to detect the temperature of an object. In this picture, you can see that the higher temperature, the brighter the color is. Well, for instance, this exposed skin, okay, dog and the human body, they have a higher temperature because they are releasing heat, which is type of energy, type of infrared light. And if you have a yellow color, that means the temperature is lower. If you have a blue color or even darker or black, that means these objects, they do not release energy, the heat. Okay, so on the infrared lights picture, they are showing a blue and black color. All right, okay, so this is the wave nature. Now let's talk about the particle nature of light. In order to demonstrate what the particle nature is for a light, we have to talk about the photoelectric effect experiment. This experiment was done a long time ago, but I think a brief discussion will help us understand why light beam shows particle nature. Well, in this is the instrument they used. Okay. Well, essentially, this is a circuit. Okay. Well, you have a battery here. You have a current meter, and you have this thing that looks like a light bulb. It's not a light bulb, but sort of like a light bulb. It has two objects. The first one is the metal here. Okay. It has a large surface. The second thing is the positive terminal. Okay. Without light, this circuit is open. It's not finished. Okay, so this meter would give you a reading of 0, because between this positive terminal and the metal here, there's no way for electron transferring between the two. Okay, so it cannot conduct any electricity. That's why the meter reading would be 0. Now, if you shoot a light on the surface of this metal, then this meter will give you a reading. Okay, so the reason is the lights will provide energy for the electrons in this metal bar to fly from the metal surface to this positive terminal. Now you can conduct electricity, and then this circuit is closed. Okay, it's finished. So you get a reading here. All right, so this is a very basic observation from this experiment. Scientists did more experiments based on this observation. Okay, they did two things. The first one is they use the same light source. Remember, okay, and the first experiment they did is they used a dim light beam to shoot this metal surface. The second experiment, they use bright light beam to shoot this metal surface. And both experiments give them the same result. That means they waited the same amount of time to see this meter to give them a reading. All right, so this is interesting because this is against the wave nature of light beam. If you think the light is the wave, then when you use a dim light, that means a weaker wave, then you would wait a little bit longer for you to see this meter with a rating that can give you a rating, right? With a stronger light, you are gonna wait a little bit shorter to see this rating here. But it's the opposite. No matter whether you are using a dim light or bright light, you waited the same amount of time. In other words, okay, this the energy of the light has nothing to do with the amplitude or the intensity of the light. It's only related to the light itself. As long as you have between the two light beams, okay, no matter what the intensity of the light beams are, as long as both light beams have the same wavelength and frequency, they will have same energy. Okay, so how do we explain it? Well, if we treat light as a particles, then this can be explained because particles, no matter how what the intensity is, if you have the particle from the same light source, or if you have a particle with the same wavelength or same frequency, they will have the same energy. Okay, so that's the reason. Now, how do we express the particle feature or particle nature of light? Here is the equation that can help us. Let me write it here. Since it's a particle, okay, now we know we call it photon. Okay, we call this the particle nature of light as photon. Okay, for each photon of a light beam, the energy of this photon equals to hc over lambda. Okay, h is a Planck constant. Okay, and that is 6.626 times 10 to the negative 34 joule per second. Okay, well, for c, okay, this c here, it's the speed of light. Okay, that is 3.00 times 10 to the 8th meter per second. Okay, this is the equation between the energy for the energy of the photon. Let's do some practice. Okay, let me write the question here. Calculate the energy of a light beam okay, with nu equals to 8.8 times 10 to the 15 hertz, 1 over second. Well, if you read this question, you know frequency. It's asking you to calculate E. Well, this equation only gives us the connection between the energy and wavelength. Okay, so how do we use the equation? Well, in other words, this equation cannot be used directly to solve this question. Well, no panic. Let's remember what we learned in the previous slides. We learned this equation, nu equals to C over lambda, right? Okay, so you have E equals to HC over lambda. Okay, well, if you reorganize the top equation a little bit, okay, you multiply lambda on two sides, nu times lambda equals to C, and then you divide the nu on two sides. That will give you lambda equals to C over nu. Okay, and then what you need to do is you plug nu into this equation. Okay, so that will give us HC over C over lambda, nu. Okay. One thing I do want to write here is if you know the math, A over B over C, that equals to A times C over B. Okay, so what we can do here in this one here, we are going to use the same way to deal with this equation. That will give you HC times nu over C. And we can cancel the C, so that will give us E equals to H nu. Okay, this equation shows us the connection between the E and the nu. So that will help us solve this problem. Okay, once you get this equation, it's going to be quite straightforward. So that means that E equals to H nu, H Planck constant 6.626 times 10 to the negative 34 joule per second times nu, that is 8.8 times 10 to the 15 1 over second. Okay. One mistake here. Okay. The unit for the Planck constant is joule times second. Okay, my bad. Okay, times second. So by multiplying both of them together, the second will be cancelled. Okay, so you will have a joule as a final unit. Okay, so the answer for this calculation is going to be 5.8 times 10 to the negative 18 joule. Two significant figures, okay, because 8.8, the frequency has two significant figures. Okay, so this is the particle nature. Well, now we learned the particle nature and wave nature of light. Based on these two natures, people developed atomic spectroscopy. Okay, and so what does that mean? It means that by using a special instrument, you can identify what element is if you have a light source. For instance, if you have a hydrogen lamp here, we know it's not hydrogen because we've already did the experiment, but just if you imagine that this is an unknown light source, by using this instrument, you can tell what's inside this, what's the sources of this light beam. Okay. Anyway, so hydrogen lamp, if you use the slit here and use a prism lane, and then you can split the lights from this lamp to a couple of different lines. Okay, and each line has has its color. Okay, and this is a hydrogen lamp, and if you use a helium lamp and barium lamp, and you will see all kinds of lines here. Okay, and for each light source, these lines are sort of like fingerprints for each source. Okay, and if you have an unknown light source, and if this atomic spectroscopy gives you the same pattern, same lines as hydrogen, oh, you will realize, okay, this unknown light source actually is a hydrogen lamp. If it gives you the same lines as the helium, then okay, you will see, okay, this is the lamp is actually a helium lamp. Okay, and in order to compare those the lamps, we have a spectrum from the visible light. The difference between the visible lights and those lamps is the white light spectrum is continuous spectrum, but for those barium helium light spectrum, you have single lines. Okay, it's because those white light comes from multiple elements. And for if you have only one element, you can see those lines, okay? Very well defined lines. All right. The last slide of this video is about the Bohr model of an atom, how we use atomic spectroscopy to verify the Bohr model of an atom. The Bohr model was developed by this young gentleman. Okay, he won the Nobel Prize when he was 37 years old, and what he did is he did some calculation and identified the possible model of hydrogen atom, and based on his model, okay, the atomic spectroscopy of hydrogen atom can be well explained. Okay, in other words, remember on the previous slide, you see those lines of hydrogen lamp, and based on his model, he explained the sources of those lines very well. Okay, for instance, at 434 nanometer, there is a violet line. And how does this the violet line come from? It comes from the energy of the electrons jumping from the high energy orbital to lower energy orbital. During this process, it's going to release this light beam. Okay, so that's why you see this violet line. For the blue or greenish line, again, it's the electron, the source of this light, the line is the electron jumping from high energy level to low energy level. Okay, for a red line, again, it's from the high energy level to lower energy level. Okay, so that's why we see different lines. In our following videos, we'll see how we do the calculation to demonstrate this different electron transition will give us different lines, okay? Because we can calculate the wavelength of those lines. And one last thing I want to mention here is Bohr model is perfect, okay, for hydrogen atom, but it has its limitation. For instance, Bohr model cannot be used to explain those multi-electron atoms. Okay, so if you use Bohr model to predict the atomic spectroscopy of helium, which has 2 electrons, that's going to be a mess. Okay, so but for hydrogen atom, Bohr model can work like a dream. Okay, all right. So this is our nature of light. Let me know if you have any questions.